lesson is on u-substitution and the chain rule kicker. So basically we're going to use u-substitution to evaluate integrals, and we're also going to convert limits of integration in a definite integral when integrating by substitution. What do I mean by u-substitution? Well, basically what happens is you get an integral that looks like this. And here we have the integral of the product 2x times the square root of x squared plus 1 dx. Unfortunately, I can't simplify anything with the square root of x squared plus 1 because of the addition in that radical. And I'm basically just kind of stuck looking at it like, I can't do this, I can't do that. And what this has happened is that I had some sort of original problem that when I took the derivative, it had a chain rule piece that's being multiplied at the end. So the formal definition of the substitution rule says if u is equal to g of x is a differentiable function whose range is an interval I and f is continuous on I, then the integral of f of g of x, g prime of x dx is equal to f, the integral of fu du. Right? You totally got all of that. So really what it's saying is we're looking for some inside layer that its derivative is on the outside. And if that's the case, then I can change my variables to u to be able to work with it. So let's look back at that same problem. First thing you're going to ask is there an obvious inside layer? To me, the most obvious inside layer is this x squared plus 1 that you see on the inside there. So what I'm going to do is say u equal to x squared plus 1. Pretty straightforward. So then du dx, the derivative of u with respect to x, is 2x. If I'm going to isolate for a second, that means du is equal to 2x dx. I just multiplied both sides by the dx. Now notice here in my original problem that I have a dx. Okay, and I also have 2x in the front, just like I have 2x dx here. So what I'm going to do is I'm going to rewrite this integral. Now, I'm going to change my variables to u's. X squared plus 1 is the same as u. So it's going to be square root of u. And then I had this 2x dx in green that I have circled in green. Well, 2x dx is the same as du. So now I have the integral of u, and I'm going to rewrite that as u to the 1/2 du. My variables in my integrand match my dummy variable there. So I can do the integral. I'm going to have 2/3 u to the 3/2 plus c. But one last problem. My actual question wasn't in terms of u, it was in terms of x. So I need to rewrite it as 2/3 x squared plus 1 quantity to the 3/2 plus c. If I want to double check to make sure that that really is my answer, take the derivative with respect to x of this. This is just confirming that I'm not making this rule up. 2/3 times 3/2 is 1. I'm going to get x squared plus 1 to the 1/2 chain rule times 2x. Is that what my original integrand was? Yes, it is. Backwards, but multiplication is commutative, so it doesn't make a difference. Let's try another one. Again, I'm going to identify an inside layer. This inside layer here, I've got x to the 4th plus 2. I'm going to say u equals x to the 4th plus 2. So du is equal to 4x cubed. Du dx is equal to 4x cubed. I'm going to have du equal to 4x cubed dx. Another way we could do this is to isolate dx by itself completely and write du 4x cubed. And what I'm going to do in that case is I'll take this dx and replace it on that entire thing. This way I'm not looking for pieces to match up. Some people like this approach better. X cubed cosine. We're going to change this to the u because that was the whole purpose here, is to get rid of that inside layer. And then this piece that I'm replacing is du to get to the variable I want, and then 4 over x cubed. And then you can see my x cubes cancel out. And then we're left with 1/4 cosine u du. Since 1/4 is a constant, I can pull that on the outside. The antiderivative of cosine is sine. That's my constant c. And then I want to replace back with my u's. So my u is x to the 4th plus 2. So we'll have 1/4 sine x to the 4th plus 2. Let's see. Here we have the third problem, and it's trickier than the last two. So the first thing I'm going to do is identify the inside layer. Okay, I've got 1 plus x squared. I'm going to have u is equal to 1 plus x squared. That means du is equal to 2x dx. Okay, so I'm going to do this more similar to how I did the first problem. I'm just going to rearrange the x to the 5th to the back for a moment. So x to the 5th I can rewrite as x to the 4th times x to the 1st. So this piece is similar to what I have for du, but I really have a one half d is equal to x dx. So I'll have the integral of 1 plus x squared x to the 4th, and then I'll change this piece to 1/2 d. Well, if I'm changing to du, so but at this point, you'll say we've got the square root of u, x to the 4th, and I can pull the 1/2 on the outside because it's a constant, du. And go, Mr. Hefke, that was great, but you still have x's in your problem. I don't see how this is making it better. Well, that's because we're going to still work with that u equals 1 plus x squared. But now I'm going to say x squared is equal to u minus 1. That's an equivalent thing if I subtract 1 from both sides. And isn't x to the 4th really just x squared squared? So now I'm going to have 1/2 the integral of the square root of u minus 1 squared du. Well, now at least everything has the correct variable. So now I've got, but we still have a product. But luckily, we have a product that we can actually combine. So I have the square root of u, I can rewrite as just u to the 1/2. And u minus 1 quantity squared, well, that's just u squared minus 2u plus 1. Still have my du. And now I'm going to just distribute that u to the 1/2 n. And now I can do the antiderivative. So 1/2 2/7 u to the 7/2 minus u 5/2, we'll have 4/5 on that, plus 2/3 u to the c. And now I'm going to distribute 1/7 u to the 7/2 minus 2/5 u to the 5/2 plus 1/3 u to the 3/2 plus c. But wait, there's more. The original problem was not in terms of u, so I need to rewrite it back to in terms of x's. So I'll have x squared plus 1, x squared plus 1, and x squared plus 1. Final answer. Now the other objective we wanted to look at today is doing the same thing with a definite integral. When we have a definite integral, okay, what we can also do is adjust the bounds of integration. So I'm going to still do my same, identify what my u would be. So we'll say u is equal to 2x plus 1. Du is 2 dx. So 1/2 du to dx. That'll be what I'll sub in. And I also want to adjust my bounds of integration. So my lower bound was when x was 0. So I'm going to plug in 0 and find out being used. You want to be careful to make sure you put them in the same spots because depending on what my function is for you, you might end up having an integral that goes from something smaller to something greater, or you might have something that goes from something greater to something smaller. So now my integral, okay, we had 0 to 4 before, and now it's going to be from 1 to 9. Okay, because when x was 0, u was 1. When x was 4, u was 9. And then I'm going to have square root of u, and then 1/2 du. So I'm changing my dx to 1/2 du. Can put the 1/2 on the outside. U 1/2. So I got u to the 3/2, 2/3 of it. It's 1/2 on the outside. That's a times. It's just really big. Plus c. Now I'm going to evaluate this at 9 and 1. So we have 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. 9 to the 3/2 is 27. A third of it is 9. And then here I have 1/3. So we're going to get 8 2/3. Or 26/3 if you like an improper fraction. Okay, this concludes today's lesson.